afternoon, everyone. Let's begin the final fight of this tournament. Before the fighting, we first introduce the jury. Please,
Good afternoon. 这个蒋志达。This is my name. I'm the physics professor of National Taiwan Normal University. Good luck.
Thank you.
各位好，我是中原物理的翁文玉，欢迎各位。
Thank you.
Good afternoon, my name is Xu Hongwei from National Single-Tone Radiation Research Center.
Thank you.
Hi, good afternoon. My name is Chang Mingguo. I'm from National Central University.
Okay. I'm the chairman of this session. My name is Taikong Zhang from National Taiwan Ocean University. Thank you. Then each team, please introduce yourself. Reporter first.
Hello everyone, we are Noniners from Typt American School. I'm the captain Darren C. and Billy Lin, Ethan Gu, Ethan Cho, and Kenneth Ngo.
Okay, thank you. And opponent, please introduce yourself.
Hello everyone, we are Team Trivial from National Giant Senior High School. My name is Fan Hao Yan. This is Su Rongxuan, Xiao Yuchen, He Cheng-You, and Huang Qingrui. Thank you.
Okay, thank you. And reviewer, please introduce yourself.
Hello everyone, this is Inaro from Kingston High School, and I'm the captain of Yikai, Zhang Yihao, Hu Jinhao, Liu Weifen, and Wang Jiehong. Thank you everyone.
Okay. Then since everyone have chosen the problem of the fight, so we begin the preparation stage. This the first part. So every team, please write down the name of the presenter on the board, please.
Chairman, 何成佑他已经当了3次的 reporter， 对啊，第一次当了3次 reporter， 所以你不能再当，你要选另外一个人，是真的很多钱，对，所以我没办法选你。好，那可以。那个，对。
13题哦，13题。
刚才跟你讲，他就知道。
就是我刚刚做
We are the opponent.
所以不用全，因为这样子需要那个音乐腔的条件，你知道要快速好，好，
对。
他们相同一下，空间上的东西，第一个，第二个，材料这些东西，第三个自己要题目，最好的题目，好的题目可能没有讲过的，3个学校。
reporter, please take a floor. You have 5 minutes.
Hello, I'm Kenneth Moore from Leonidas, and today I'll be presenting concept in continuous heat. So the pump statement states that a glass tube with a sealed top is filled with water and mounted vertically. The bottom end of the tube is immersed in a beaker of water, and a short segment of the tube is heated. Investigate and explain the periodic motion of the water and any vapor bubbles observed. So our main focuses today will be what is the mechanism responsible for the water's periodic motion, and the vapor bubbles oscillation, and also the vapor bubbles maximum volume. So here are some observations. Here's our experimental setup. We seal the top of the tube with a cork sealer, and we heat the tube with a DC generator connected to a coil, and we use a temperature probe connected to logger probe connected to the tube. And we notice that there are 3 phenomenon types depending on heating to water volume ratio. The first type is when there's a high heating to water volume ratio, where a single vapor bubble spontaneously forms. The second, where there's a medium heating to water volume ratio, there's a lot of bubbles forming, but not one singular vapor bubble. And type 3, with a low ratio, there aren't any bubbles at all. So we'll be focusing on type 1, as we believe that's what the problem statement is asking for, since only type 1 has a periodic motion of the bubble. So here's our model. This is a graph of our volume of the bubble versus time. As you can see, it is periodic. And our first part of our explanation will be the heating phase, where it goes from no vapor bubbles to vapor bubble formation. The requirements of this phase will be that coil heating rate is greater than the environmental cooling rate. So more heat is going into the tube than leaving it. And tube water at coil segment must be at 100 degrees Celsius, which is the boiling point of water. And spontaneous bubble formation speed must be greater than the velocity of the bubble that's running from the tube. And here are some of the factors for heating. We need the water to boil very fast so that there is a quick bubble formation and expansion. And so there are 3 types of heating. First, where the coil touches the glass properly, there is conduction heating between the coil and the glass. And where it doesn't touch so well, there is radiation heating. And the glass then heats the water and or water vapor through conduction. So, despite our general conception that objects of lower density, such as bubbles, rise, since the top of the tube is sealed and water is incompressible, the bubble has no route of expansion except downwards. However, there is consistent water slippage down the side of the tube during bubble expansion, so there is still a small velocity upwards. So as you can see from our graph here, there is a high velocity downwards and a lower velocity upwards. And after the heating phase is a cooling phase, where the bubble goes from its maximum volume down back to its original equilibrium size. So the requirements are that the net environmental cooling be greater than the coil heating rate. Here you can see the bubble shrinking. And there are several factors that affect the cooling during this phase. For example, at the ends of the bubble, there is conduction between the rest of the water in the tube and the vapor. And there is convective heat transfer from the water that slips down the tube, as we mentioned previously. And there is also conductive heat transfer from the glass tube, basically the environment cooling down the water vapor. So here's our quantitative model. We relate the change in volume per time to the change in energy per time. And the change in energy per time we define as the amount of heat gained versus minus the amount of heat lost to cooling. So the amount of heat gained will be from our coil. So I squared R is the power given by the coil. And we multiply by constant since there is heat lost and not all the heat is transferred into the tube. And for our cooling, we have the various conductive cooling from other outside sources. And if we apply Fourier's law of heat conduction, the above equation transforms into the downwards one. And since alpha kappa, which is our heating efficiency constant, is hard to determine theoretically, we will determine it experimentally. So to determine the constant alpha kappa, we isolate it from the previous equation, and we relate it to the volume of the bubble versus the volume of the coil that's heated by the coil to experimentally determine it. So as you can see, it is a downwards trend. And since the efficiency is dependent on how much water or vapor is exposed to the coil. At the very start, the coil is 100% heating water and 0% heating vapor. since water has a much higher thermal conductive constant, the heating efficiency will be at its maximum. As the water starts to evaporate and turn into vapor, the efficiency will decrease. And as you can see towards the end, where the coil is 100% heating water, vapor is 0% heating water, the efficiency will approach 0% because the thermal conductive coefficient of vapor is very low. And so to verify our experimentally determined constant, we took the constant when it's heating all water versus the constant when it's heating all vapor, and we found that to be about 22.6. We compared that to the ratio between the thermal conductivity of water and thermal conductivity of vapor, which is 25.4, and we find that it is roughly similar. And there's slight error because, as we said before, there's water slipping down the tube. So when we're heating all vapor, it's not really all vapor, we're still heating some water. So the efficiency will be higher here, and therefore this number will be a little bit lower than expected. So next, we have to determine vapor bubble pressure, PG. So since there's constantly an atmospheric pressure pushing down on the sides of the beaker, there will also be a constant atmospheric pressure pushing upwards into the tube. And there is also downwards pressure from the bubble since it expands downwards, and the rho GH pressure from the rest of the water in the tube. So those combined have to be equal to rho HV, and instead of a gravitational acceleration, we take the acceleration of the center of mass of the vapor bubble, which we define as 1/2 times the double derivative of HV per time. And here is that equation under a few initial circumstances. So we can also make a few assumptions. We assume negligible convective cooling from slipping water from the top of the vapor bubble, and we assume vapor bubble covers the total volume of Typt region. So, which is to say, we model the vapor bubble as a cylinder. And we assume there is uniform heat flux from coil, and that the bubble expansion starts when coil segment of water is 100 degrees Celsius. So, to verify here's our reasoning behind assumption 1. Since the water slips down from the edge between water vapor and the water, we can assume that the water that slips down is just below the temperature of the water vapor. And that's why, And then we also calculated the volume of the water that slips down, and we found it to be this number, which is extremely small. So these two combined mean that we can basically ignore the cooling from that water. And our assumption 2 is that we can model the bubble as a cylinder. So we calculated the volume of a bubble, like the complete bubble as a cylinder, and then we calculated the volume without that top half circle part. And we found the ratio to be about 97.2%, meaning that it's like basically the same size, and we can just assume that it's cylindrical. So our assumption 3 is that there is uniform heat flux from the coil, since we wrapped it in proper uniformly segmented solenoid structure. And our last assumption is that the bubble expansion starts when water at coil segment is uniformly 100 degrees, since that is the boiling point of water. And our theory basically works like after that point, after this assumption. So here are a couple of experimental parameters. First, we tested the coil distance from the top, basically moving the coil downwards. And the greater the coil distance from the top, there will be a smaller distance HB between the water in the beaker and the coil. So therefore, the water in the beaker can more effectively cool the vapor bubble, and therefore we will have a smaller maximum volume as seen from this part of our equation. And our trend line seems to suggest that this is true. So, however, there is some error. Since we manually moved the coil with our hands, the coil slightly loosens as we move it up and down. So, as we said before, some of the conductive heating between the glass and the coil will be transferred into radiation heating. So our efficiency constant will decrease a little bit. And then we tested immersion depth. So as we immersed it more in the water, it's the same as before, where the distance between the beaker water and the coil will decrease. And therefore, there will be a higher cooling rate and a smaller maximum volume. Our graph, once again, suggests that this is true. However, there is some error because as we immerse the tube more and more into water, it will be harder to insert the temperature probe, and so the temperature will be slightly inaccurate. Then we tested coil power. So obviously, with a higher as seen from that part of our equation, a higher coil power will mean a higher heating rate, and therefore the maximum volume of the bubble will increase. And as from our trend line, this is true. However, there is also some error because you can see from our previous slide that our first data point has slightly larger error. That is because it's a very low wattage, and so it doesn't heat the water up very fast. So the hot water can, through convection, can go to other places and like the temperature kind of balances out. And when it's less than 7 watts, we find that our type 1 phenomenon turns into type 2 phenomenon since heating is much less efficient. We then tested heat tube size. As we increases the radius of our tube, the heating will be less efficient and there will be more cooling, so the bubble will shrink faster. And as we increase the tube even more, you can see that it turns into a type 2 phenomenon since individual bubbles rise faster than spontaneous bubble formation. So, in conclusion, we find that there are 3 phenomenon types depending on heating to water volume ratio, and we decide to focus on type 1 as we believe that's what the question statement is asking. And our theory can predict the change in volume per time depending on heating factors, which is the change in energy per time. And we correlated experimental parameters such as coil position, immersion depth, coil power, and heat tube size with our theory, and we found our theory to be rather effective, I guess. Yeah, here are our citations, and thank you.
Okay, thank you. And opponent, you can ask questions to the reporter. You have 2 minutes.
Hello, I'm the opponent of this problem, and so I want to ask, do you think putting your thermometer into your the tube has any effect on your result?
I think it's negative. Yeah.
Not good. So do you test the result without the thermometer inside?
I don't think so because we think that like the thermometer is quite like.
And how do you track the bubble using tracker?
Yeah.
And is it accurate?
I think it's very accurate.
Okay, but so did you manually control the accuracy? Like if the tracker doesn't detect the bubble?
Oh yeah, we tracked it by hand.
Okay. Okay, so this is
Okay. Opponent, you have 3 minutes to prepare the presentation.
Chairman, next speaker.
So, however, I'm the opponent from Team Trivial of this problem. Okay, so the problem statement is as follows. A glass tube with a sealed top is filled with water and mounted vertically. And the bottom end of the tube is immersed in a beaker of water and the short segment of the tube is heated. And investigate the periodic motion of the water and any vapor bubbles observed. Water. And the key points are what are some of the periodic motion investigated, and second, what behavior do the bubbles have, and third, are there boundary conditions that cause some phenomena to happen. This is a quick overview of my report. And so, and the overview of the report for the phenomenon, the reporter shows various parameters and the clear image of the apparatus, and also there are some visual demos. And for the theory, they make qualitative analysis out of theoretical derivation. And also they consider the details such as the heat dissipation. And for experiments, they have some explanation of data and analysis too. Okay, so the advantage of the reporter is that he successfully created the phenomenon. And also they have great experimental setup and also the good time management. And for the suggestions, we think that this reporter should put more emphasis on the parameter overview because they use a lot of symbols and numbers in their theoretical model. And also they should focus more on the boundary conditions, which we'll ask them later. And maybe put more emphasis on the equations and the relations between the vectors. Also, they should focus on the periodic motion form. And also, we think that they may have some misunderstanding on the problem statements. And maybe you could be louder and slower and more clear too. And okay, so also we want to emphasize that maybe the water will have an upward motion, which I think you haven't mentioned. Okay, and so there are more about that, and so it's, for example, the more explanation of the three phases, you just discuss one of the phases. Okay, so for the third question, I asked, did you think that putting the thermometer into the tube has any effect? And the answer from the reporter was no. And how are the bubbles tracked? And they say they use tracker, and I think it's accurate enough to track bubbles using tracker. Okay, so I want to move on to discussion.
Oh, please go ahead.
Okay. So first of all, I want to ask problem number 2. Do you think that the gas behavior can be explained as the ideal gas equation?
Actually, yes. Well, our quantitative model isn't exactly derived from the ideal gas equation, but there are several parts from the ideal gas equation. For example, you can see the pressure here, the temperature here, and then this L and M are like the latent heat and the molar mass of water. So we did kind of incorporate the ideal gas equation into our theory. We just didn't use it directly.
Okay, so maybe you can point out more about what you applied onto your model.
So
more clearly, for the I think you just emphasize on the heat part,
Okay, yeah. So the heat, we think the periodic motion is based on this, right? So basically the change in volume per time, and however here we have this term pressure, because the pressure of the vapor bubble, as seen from the ideal gas equation, will affect kind of the motion and the change in volume. And here's the latent heat, as in how easily or how effectively the water or the bubble can be heated. And then the molar mass is kind of with the latent heat to determine that. And then we also include temperature and the R, which is the ideal gas constant into our.
Okay. So what I want to ask next is, are the pressure difference and temperature difference on the other tube, the long tube? Are there any differences from the bottom to the top that you'll consider?
Sorry, could you like rephrase that a little bit?
Okay, so what I want to ask was, so can you put one of your experimental thing? Yeah, so okay, so like at the bottom and the top, there's some pressure difference and also the temperature difference.
I think
Is that enough to affect?
I don't think so. I think the main part is still like the coil, and I guess the position of the coil also affects it, and the position of the coil would affect like how different the temperature and pressure is. But we also did include our upper. Basically, we included the pressure of the upper part and the pressure of the lower part. So we do think there is an effect, and we put it into our theory.
How about the temperature?
Temperature, yeah, like as I said before, this term is the temperature, is the cooling that the water will have on the vapor, and this term here is the cooling that the bottom part of water will have on the vapor. So we also think that there is an effect.
And so, do you have exactly the number on the bottom and the top?
Well, it's different for every experiment, but like.
So at a single experiment, do you get the bottom and the top?
I don't think we have like isolated data for a single experiment.
Yeah, things you put your thermometer like inside the tube.
Well, we kind of. Well, we use these to like basically we calculated this entire thing. Like we didn't. I guess we have to like we don't have it right now like the separate parts of our tube. So we just like calculated this and then calculated this and then compared them.
So you did get the temperature.
Yes.
Okay.
Sorry.
And so you're okay. So next question. You're supposing that the vapor bubble forms when the water is on 100 degrees Celsius.
Yeah, 100 or more.
And did you consider the effect of bumping? Like since you are using a clean gas tube, do I have to explain what's bumping?
Sure. Okay.
So, as you can see, bumping is a phenomenon in chemistry where liquids boil in the test tube or other container with superheat and rapidly boil. So, if the water was higher than 100 degrees, however, it will not boil at the moment because your tube was too clean.
Well, I don't think we put in enough heat for bumping to happen. So I think for our experiments, mainly like the normal thing happened where it like just like starts to boil from the middle and then like water gets turned into water vapor from the middle.
So are you sure about it's just boil, not bump?
Yeah, we're pretty sure. I don't think that happened in our experiment.
So how do you prove this? Like, is your thermometer just get 100 degrees, not above?
Sorry. Could you?
So sorry. Okay, I also want to ask one question. That your thermometer, what part is it sensing when you're doing this experiment?
I think we track like different parts for different experiments because as you can see, like we have to know the temperature of this upper part, the temperature of this lower part, and the temperature of the bubble. So
you keep moving the thermometer.
yeah, so like we have different trials where we like test different parts of it.
So you just keep like pushing it inside.
Or sort of like, but we do the experiment multiple times and then test different parts of it. And the different parts we also test multiple times so that we know it's accurate.
Okay. Okay, I get it. And so for the experimental part, I want to ask that are the water temperature and the room temperature controlled?
Well, it's not really controlled, but we can assume since like the temperature range is so large that like, I mean, room temperature is like about that range, right? Like it can't vary too much, and since like the difference in temperature is like so huge, we don't think that would have too big of an effect. But yeah, you're right. I think we should control the temperature better in the future. Like that would make the experiment better.
Okay. And so are the bubbles all composed of water vapor? Are there any other components?
And so we believe it's composed of water vapor because you heat up the water, right? So if water evaporates, then obviously it turns into water vapor.
So there's none other.
We don't believe so.
But as you heat up the water vapor, there will be some bubbles appearing before the boiling.
Oh, we can expand. Oh yeah. Remember when we have like phenomenon type, right? So for type 1 we had like a one singular bubble forming, and I think you mean like type 2, right? Where like bubbles form before the main one forms.
Can you explain about the type 2?
Type 2 is like well, so basically where like smaller individual bubbles form first. Is that what you're talking about? Like
I'm not
bubbles
sure.
form before.
So you suppose the little bubbles that form first are the other gases that's diluted in the water.
Yeah, we think this is also water vapor because basically can go to blue.
Yeah.
So let's say you have this tube, right? Since you have a medium heating to water volume ratio, basically what it does is that the coil heats up the tube, but it doesn't heat it up fast enough so that like the water that gets heated kind of like does convection and it goes to other spaces within the tube. So in this case, we will have the entire tube of water will be heated up before. Oh, so type 1 is like only this part is heated up very fast and what the old one. Type 2, since heating is less efficient, the entire tube of water gets heated up first. So then like bubbles start forming like throughout the entire tube. And there's no like one singular, but we still think it's water.
What's the temperature when the bubble forms?
Probably around 100 as well.
So the whole tube was 100 degrees.
Well, maybe not the whole tube, but like a larger part. That's not just like this part.
It heats up the whole tube first and the bubble forms.
Yeah, so, well, maybe not the, but like a larger part of the tube, basically. Not just like this.
So just larger than
Yeah, yeah. And so, yeah, that's how you distinguish between the difference.
So I think maybe you can put more description on type 2 and type 3.
Oh, yeah, I think, yeah, that's better.
Okay. Okay, so this is all.
Okay. Opponent, please summarize the discussion. You have 1 minute.
Okay, so for the theoretical part, we discussed about the gas behavior of the experiment, and as the reporter doesn't really explain much about their theoretical part, so I think we accidentally neglect that maybe they have used the ideal gas equation, but we just didn't get it at the report part. So we are sure that, and also we discussed about the difference about the tube at the bottom to the top, about of the pressure and the temperature difference, and also we discussed about the whether there will be bumping or not in the tube, and also for the experimental part, we asked that the temperature in the room and the water was controlled or not, and the reviewer said no.
Okay, Tom, yes. So, review, next question to the reporter and opponent. You have 3 minutes. Please go ahead.
Okay, thank you for the opponent and the reporter. So, I want to ask Coach, the type 3 is the water surface in the tube oscillates, right? Yes. Why? Because like it's kind of like it's getting heated up, so some evaporate and then cool down, and getting heated up and cool down. So we didn't investigate because we thought that there was no like. What do you think about it?
Yeah, we agree with the report.
Okay, but I also wonder what will happen after the type 3. I don't think much happens. Like, if you continue to lower the heating to water volume ratio, it should like we continue giving it energy. What will happen? It just keeps doing that. So. And if you lower that ratio even more, there wouldn't be enough heating to evaporate the water. So what do you think about this question?
I think it should be further investigated. What's the part that the reporter didn't mention?
Okay, and the type 1 and the noise when you heat it and the highest part of the tube, there should be a temperature difference. So will it influence the results of this experiment? Well, you mean like from here to the top or from here to yeah, whatever. Yeah, that temperature difference is what cools down the vapor bubble. So like it will so, and what do you think?
Okay, so I think the bubble comes out first, and it may vanish as the bubble goes off the tube.
Okay, have you tried to analyze the temperature just at the coil line and just under the temperature are the same or just different? Temperature from coil line to the there and there are they the same? Oh, they're not the same because the coil is heating up this part, so this part will obviously be much hotter, and this part, since there's nothing heating it, it will be like less hot. Okay, and what do you think?
Yeah, we agree that coil.
So will it have any effect?
You mean what?
The temperature difference.
You mean at the bottom of the
Okay. And I think that's it.
Okay. So review, we have 2 minutes for preparation. Okay, the review, please take the floor. You have 4 minutes.
Okay, thank you review for the opponent and the reporter, and I'll review for the carbon 13 colonial T2 in this scenario. And okay, here's the problem statement. It says a glass tube with the seal top is filled with hot water and mounted vertically. The bottom end of the tube is immersed in a beaker of water, and the short segment of the tube is heated. And they investigate and explain the periodic motion of the water and any vapor bubbles observed. And here's the performance of the reporter. They for the theory part have explanation of bubble, and for experiment they have good use of media which can make me understand more about how they did it. And for the conclusion, they connected the theory and the experiment together. And for pros, they have quite clear explanation about the theory, and they explain the bubble from different parameters, and good time management. They also explain. Okay, and for the cons, I think, in my opinion, they should put more focus on the water's period, not the bubbles period. And yes, I think this is a critical part of the problem, so maybe they have a misunderstanding of the problem. And for the performance of the opponent, they have a bit better understanding of the question, and they have a good discussion about the pressure and the tube with the reporters. However, they have poor time management, and they did not point out the real question of the reporter. And here's their discussion topic. The first, the opponent asks the pressure at different parts of the tube. The reporter says they have shown it in the report. And judging from this question, I think the opponent should put more focus to the reporter's report. And here's the second one. This opponent asks which part is sense, and the reporter clearly explained their setup, and their explanation is quite clear. And I think they can also discuss more about the data and the experiment, not just this part. And here's the third part, and the opponent asks temperature control, and the reporter says they will control in the future. I think it's quite good for the opponent to find out this question, and for the reporter to discover their question and will improve it in the future. And that's here is where point meets. They haven't discussed about what will happen after the type 3. And because they mostly want to discuss about the water's period. And if you keep eating what will happen, perhaps the water's period will appear. And the last one is, will temperature difference have an impact to the phenomenon or the results of this experiment? And I think that's it. This is a review for 30.02. Thank you everyone for listening.
Okay. So reporter, please take the floor.
Well, I think what happens after type 3, since we define type by like heating to water volume ratio, if we continue to lower that, then there wouldn't be enough heating to like form vapor, and also like it would just be water. And so concluding remarks are that we inserted the thermometer into the tube, and it allows for accurate measuring of the temperature, and we should try to control environmental temperature. The opponent makes a great point, but we think it's like relatively negligible. And we track by hand, and we believe it's very accurate. We track the top and bottom of the bubbles, and we incorporated sections of the ideal gas law into our quantitative model, such as like temperature, pressure, molar mass, and whatnot. And we accounted for differences in coil placements, so we included the pressure and temperature of like the upper and lower sections of our of the tube into our theory. And we also did calculate the temperature. And we don't believe that enough heat was added for bumping to happen. And we tested the temperature of different sections of the tube in different trials, and we repeated it to ensure more accuracy. And the smaller bubbles that occur in type 2 we believe are made of water vapor still, since like there's only water in the tube. So yeah. And type 2 occurs due to the heating efficiency being lower, so a larger part of the tube will be heated up instead of like just a small part. And we believe that in type 3 water is also periodic, but we didn't investigate it since there was no bubbles, which means that we didn't think it really fit the problem statement, which asks for like a bubble. Yeah, that's it. Thank you.
Okay. So it's time for the question of the jury. So, any question for the jury? Professor Wilkins?
A question for me. You mentioned most focus on this water or bubble in the tube. Have you ever have observation on the beaker? Is the water level on the beaker changing anyway?
Yes, because as the vapor bubble expands, it kind of displaces water, so then the beaker, like it displaces water in the tube so that the beaker water will like rise a little bit. But like we think since the beaker has so much more water compared to the tube, it wouldn't like oscillate very much. Like maybe only a tiny bit.
So you're saying that in your, for example, in your equation, you don't really think about anything happening in the beaker.
No. Well, just like the position of the beaker and like how that affects the cooling of the tube. That's like the only part.
So that included in your formula?
Yeah. Like we included the distance between the coil and the beaker water. But since we think it doesn't change that much, we kept that as like constant, not very.
I agree with the reporter since the surface area of the beaker is much larger than the tube they use. I think the height was negligible.
If you ask about extend to the water surface in the beaker, then perhaps you will have a little energy loss. So it should be also taken into consideration.
No, I can have a second. Maybe you first.
It's okay. Just go.
I just follow the question because this poem is big tube, and I suppose it is from this movie, right? So this is some kind of engine driven by the heat. So the engine is driving the boat. So how do you think about this setup? Is anything can do any work driving something using this mechanism, heating mechanism? Yeah, anyone?
I think like at the size that we experimented with, it can't really like move anything because it's a very small amount of water and vapor. But if we like maybe enlarge it, then I think it can possibly like do some work on like maybe some motors or whatnot.
Yeah, I think if the experiment setup was large enough, then the bubble rising can generate electricity from pushing upward, and maybe it can be able to push the boat.
When it comes to the type 3, all the water will get out, and then the boat will move more if then just the bubble gets out. So I think this is how O'Neill's boat moves forward.
Okay. For reporters' presentation, you two had challenged about the motion, periodic motion of the water. Can you explain to them about the motion of the water, or you have any comments on the motion of the water, or the opponent and the reviewer?
I think the periodic motion we mainly considered was that like the water gets heated up, so it gets turned into bubble, and then it gets cooled down and then collapses again. And then after a while, the same thing happens again. So basically, a bubble appears and then shrinks, and then appears and shrinks again in a periodic motion. And
So I think the motion is a part of the phase 3, that the water will come out from all of the tube.
But they discussed type 1.
Yeah, I
Type
know,
1.
but I think I mentioned about it. Like maybe they should also discuss about type 1 because that's
From their report, can you comment on the motion of the water?
so. I think type 1, the water motion is only when the bubble comes up to the top of the tube. It will the additional pressure of the gas of the water vapor will push the water.
Okay, how about reviewer?
In the report, I see the main focus is on the motion of the bubbles, not the should investigate all the three types.
Okay, thank you very much. Thank you.
Okay, now it's time for Julie and story. So let's show the score report. 8, 6, 6, 8, and 8.
8, 6, 6, 8.
Okay. I will show the score for the opponent. 8, 7, 6, 7, and 8.
8, 7, 6, 8, 7, 8.
I will show the score for the reviewer. 7, 6, 5, 6, and 6.
7, 6, 5, 6, 6.
Okay. Any comment from jury?
Pretty sure that this is the last fight on this problem probably. So I was asking the motion in the beaker because the beaker, water in the beaker go up and down. It basically is done by some force, so he has a work. He received the work. So, and there's as you already say, you have the heating, right? And the heat also dissipated. So the difference of this heat ratio give you this value. And so this is there's a heat coming, there's a heat come out, but not all the heat come out because they done some work. That's why it's engine. So it's more like heat engine. So maybe you can think about this question as like some kind of heat engine. So there's energy coming, energy come out, but there's some energy doing some work to prevent the bubble or the water up and down with this dissolving motion. So let's give you another point of view to think about this question.
Okay, thanks, Professor Wood. Any comments further? No? Then we close this section and we come back in 10 minutes. Okay. So each team please take the rotation of the position 5 of this element. Each team please write down the presenter's name on the board. And report on your 5 minutes for the observation. So please write down the name of the presenter on the board. reporter. Okay. Okay. Oh, please take the floor.
Hello everyone, I'm the reporter of Interview, and today I'm going to report problem 3, the siren. And here is the problem statement. If you direct an airflow onto a rotating disk with holes, a sound may be heard. Explain this phenomenon and investigate how the sound characteristics depend on the relevant parameters. So here is our overview of the report. There will be 5 parts of the report: introduction, experimental setup, theoretical model, experiment, and conclusion. The first part is the experiment setup. Okay, this is our experiment setup. We use DC motor to drive the disk. Then we use air lens to produce and steady airflow. Finally, we use microphone to record the sound and analyze with the computer. Here's our disks. We made different disks with acrylics and we drill hole on it, and we totally made 7 disks. And here's the table of the size. Okay. This is the phenomenon of the siren. Oh, as you can hear the harmonic of the siren, and the harmonic is the integral multiple of the fundamental frequency. And this is our measurement method. We use this software to measure the frequency of the sound. And this software is Voice Pro. And we record the peak frequency of different disks. And to analyze the harmonics, the composition of the harmonics, we record the background noise and the experiment data, and we subtract the noise from the data to get the composition of the harmonics like this graph. And next one, we want to know the relationship between the rotating speed and the voltage of the power supply. So we stick a sticker on the disk. Then we use high-speed camera to record the turning situation of the disk of different voltage. Then we use tracker to track the rotating speed of it. Here's our parameters. There will be 5 parameters of the siren. First one is number of holes, and rotating speed, and airflow speed, and radius of holes, and size of holes. This is our theoretical model. And the first one, this is a sketch of the siren. The red circle means the holes, and the blue circle means the airflow. We assume the holes, the diameter is the same as the airflows. Then we can calculate the overlapping area of 2 circles like this, where A means the diameter of the circle, and G means the distance between 2 centers of the circle. Okay. So we can describe the relationship between airflow volume within that is related to A, and time within that is related to D, like this pattern. And if we increase the rotating speed or increase the numbers of poles, we can get more intensive patterns. So we can get the frequency is proportional to the rotating speed and the number of poles. So finally, we can get the relationship between frequency, the rotating speed, and the number of poles. F first is equal to omega revolution per second multiplied by n. Okay. So the result above is just about the fundamental frequency. The harmonics we refer to the reference. So this is the reference. According to the reference, we can analyze the composition of the harmonics like this table. And this chart is the result of the reference. And when A divided by L, if A is the diameter of hole, L is the distance between two holes, and A divided by L is smaller, the harmonics n equal to 2, 3 or other, is louder like this blue one, and vice versa. Okay, this is our experiment result. First, we define some symbols of the parameters. N is number of holes. Omega is the rotating speed. V is the airflow speed. Uppercase R is the radius of holes, and lowercase r is the size of holes. And the theoretical frequency is equal to n multiplied by omega. First one, number of holes. The chart shows the result of different number of holes, and this frequency is the fundamental frequency. Okay, so the blue line is the theoretical frequency, and orange line is the actual frequency. And the second one is the different rotating speed. The rotating speed is transformed from the voltage of the power supply, and the chart shows the result. And the data above, you can see it is approximately smaller than the theoretical frequency. We think that is because the strong airflow will make the rotating speed decrease. So the data above is smaller than the theoretical value. And it makes the frequency smaller about 3.4%. And we try the different airflow speed, and as you can see, the strong airflow speed, the frequency will decrease. Okay, so this is the result of the experiment 1. And the fourth one is the radius of holes. This is the different harmonics of different groups, and the blue line means A divided by L is smaller. The harmonics decay slowly, as you can see. And the yellow line means A divided by L is bigger, so the harmonics decay quickly. It confirms the theoretical prediction. And the last one is the size of holes. As you can see, the blue line means A divided by L is smaller. The harmonics decay slowly. And the gray line means A divided by L is bigger. The harmonics decay quickly. And it still confirms the theoretical prediction. Okay, for our conclusion, first one, frequency is equal to rotating speed multiplied by number of holes. And the strong airflow will make the frequency smaller than the theory. And last one, the harmonics depend on the radius of holes and the size of holes. That's my presentation. Thank you for listening.
Okay, thank you. So opponent, please ask question to the reporter.
Okay, thanks for Dr. And my first question is, how do you get the hole on the piece? How do you make the hole on the piece?
We use laser cutting machine to make the disc.
Okay, and what kind of the material what's the piece of the material of the disc?
It is made with acrylic.
Okay, and number 5. Page 5.
Page 5.
So the power split and what do you use it to do?
We use it to supply the electricity for the motor.
And that you have mentioned you have take off the noise, right?
Yes.
And how do you notice the noise of the tape?
And we make the experiment that don't have the sound, so we think that is the noises of the background. It excludes the motor sound and the airflow sound.
So you have found a place that is higher to do the experiment. Page 6.
Your time is up. The opponent, you have 3 minutes for preparation. owners, please take the floor. Please speak louder in the discussion.
Okay, now I'm going to ask problem 3, siren. And this is the test. If you direct an airflow onto a rotating disk with pulse, the sound may be here. Explain this phenomenon and investigate how the sound quality depends on the relevant parameters. And the structure of solving the problem is that they define different variables, then they do experiment, then finally find out the frequency of the sound. And the course of the report is that the theoretical molecular literature and simple understandable qualitative expression of the experiment and the use of media. And the count is that the lacking explanation of the data and computation of the frequency of different parameters, and they also missing investigation of some more variables such as the angle of the airflow. And the cost of the experiment is that the background and reproducible setup and investigation of the phenomenon and combination of some variables. And the count is that the parameters there have some parameters not mentioned and we will discuss later. And the second is that the non-measurement of the thickness of the disk and missing investigation of the noise. And the cost of the theory is that the relevant model of the how the stellar is designed and on coefficient of the airflow. And the comment is that they compare how modification of the theory was actually done and institution model how why different variables will influence the frequency. And this 4 points is that I will discuss with Dr. later. First, we will discuss when we change the place of the hole will affect the experiment result or not. And second, we want to discuss how the sound is created. And third, we want to discuss the angle of the airflow. And next, we will discuss the radius of the pulse.
Okay, so please go ahead for the discussion.
Okay, first I want to discuss this that have you changed the different place of the hole?
Different place of the hole, like the radius of hole.
Can you
mean for?
Yeah, please go ahead.
Move the ball to near the boundary, or you make it near the center.
We have done this means that this one the ball is this one radius of pulse.
And
To the center.
can you explain this graph?
Okay, so as you can see, the green, blue line is the
radius of the hole.
yes to the center. This is 80 millimeters. Then you can see the theory if A divided by L. We think that they were outside the disk, and so the L is larger. So the A divided by L is smaller. So the harmonics decay slowly and the yellow line is A divided by L is bigger. So harmonics decay quickly.
And I want to know why this line is not a linear. Why it has higher income? explain this?
The experiment error. So we just discuss the trend of the line, not the actual value of the experience.
Okay. And second, I want to know how make the voice.
How many voice?
Yes.
We think that is the air make the voice loud. This one. So okay, the blue is airflow, right? And the red is the hose. And as you can see, the hose to this place, the airflow pass the hole, and this way the airflow don't pass the disc, so you will have periodic change. So we think that is the frequency of the sound.
So you mean if the air pass the hole, it will have voice, right?
And pass and not pass and not pass and not pass. The change.
And have you investigated because in my opinion, if the velocity of the rotation too slow level, you can't hear the voice.
You are right. So because the frequency is too low, so we can't hear the voice.
So you have investigated this.
We just consider the next one is so if the rotating speed is lower, we didn't try it.
So in this data, which voice you can hear?
We all can hear this is 640, so we can hear it.
So here is no data that the frequency you can hear. And have you said you use the airflow to pass the hole on the disc, right? And have you changed the different degree to let the airflow pass the hole?
You mean different angle?
Yes.
We didn't try it, but I think that will affect this blue circle. It will be more bigger, so the area between two circles will change.
And after this, what do you think the frequency will change, will increase or no?
The frequency won't change, but I think the loudness will decrease. The airflow.
This airflow will increase.
And the volume
So you mean the voice will become louder?
decrease.
And if you have your experiments investigate the different size of the hole?
Different size of the hole.
Yes. Yes. And can you explain these photos?
Okay, the blue line is the smaller size of hole, and 2 millimeters. So A divided by L, A is smaller. So the harmonics decay slowly and this gray line is 6 millimeters. So the A is bigger, so A divided by L is bigger. The harmonics decay is big.
And here, both of the green and the gray line have increased, and yes, decreased. And but the blue line have obviously moved.
I think that is because the size of hole also affects the volume, and also the biggest hole it has loud volume, and the blue line has the small volume, so it's like a horizontal line.
You say you have changed the velocity of the wind, the airflow, right? Yes. Can you go there? So, can you tell me how long you use the airflow to pass the hole?
You mean the distance between the air length and the disc?
No, and it means how much airflow you blow through the hole.
How much? The actual. We think that the airflow speed is complicated to measure. So we just consider the low, medium, and high.
And you say you change the size of the hole. Increase the size of the hole, and example, this is the area you are airflow. If you increase the size of the hole may like this, smaller than the area of the step or bigger, right? And how will it affect
The question just as the airflow diameter is bigger than the holes, and if you consider that this one, you mean they are different, so the blue circle and the red circle size is different, but we still can calculate the area between overlapping area.
Yes, I want to know how will it affect your experiment research. Have you investigated this? Okay, no. Can you explain this phenomenon? Why change the size of the hole will also change your, also affect your experiment research?
Size of holes.
Yes.
If I'm sure.
Okay, time is up. So the opponent, please summarize the discussion. Give me 1 minute. Please.
In the 10 minutes, I discussed some topics with the total. First, we discussed the test of the hole will affect the experience with you or not, and the reporter said yes. And second, we discussed how the sound is created, and the reporter said because the airflow pass the hole or not, and then they will create the noise. But I think this is not enough to explain this phenomenon. And second, we discussed the angle of the floor. And the reporter know that the
Okay, time is up. So review presents question to the reporter and opponents.
So first for the reporter, wait, can you put up the slide again? I have some questions for you. Setup. So first of all, what do you think are the relevant parameters in this experiment?
I think the velocity of the airflow, or the velocity of the location, or the size of the, or the less many parameters will affect this experiment.
Okay. And do you think like background noise can lead to some disturbances in their experimental data?
You know how they take off the noise?
Yeah.
Yes, they say.
Do you think that it might decrease some of the amplitude of the frequencies?
I think they can just find a correct place to do this experiment and
Okay, thank you.
take off the noise.
So can you go to your experimental setup demonstration video? Wait. So the demonstration video. So okay, wait. So when you held so you were holding this thing, right? So do you think that when the movement of your hand may affect the position of the airflow?
I don't think so. I think the distance between my airlines and this is constant.
Okay. And so I still don't really understand your definition or why you think this phenomenon happens. Can you explain it more clearly, qualitatively? Or can you explain it, the phenomenon?
I think the airflow goes through the holes and blocked by the this goes.
Do you know like what sound? Do you have a short definition of sound? Do you have a definition of sound?
I think the sound is inside that can hear by us.
Okay. And you, the reporter?
What do you mean about the?
Okay. It doesn't matter. Can you go back to the slide for the A and L? Can you define A and L? Oh, it's okay. Okay. Okay, so do you think that the shape of the hole will affect your data?
Sure.
What-
It will affect the overlapping area. The overlapping area.
Then what do you think the shape of the hole would affect in terms of the sound characteristics?
Okay, so time is up. So review, you have 2 minutes for the preparation.
Okay, so I am Darren C. from No Nigers, and today I will be reviewing number 3 siren disc. Okay, so if you just go to the next slide. So for the reporter, so positives are that they had showed a clip of their experiment. They had tested multiple parameters. They had a basic quantitative theory, had experimental data, and mentioned a harmonic theory. So for the improvements, they had many setup errors, possible big errors such as their position of the air hose, which they used their hand for. They did not have a qualitative explanation of it, or their qualitative explanation was insufficient. They did not bring up effects of vortices or turbulence, which we think is very important. They did not investigate the shape of the wave that they reported, and there were no error bars and very little error analysis. And so for the opponent, they brought up the angle of the airflow, which was good because it was a parameter. They brought up the need for a better model with more parameters as well. And so for the improvements, they did not bring up enough parameters. They did not bring up the turbulence effects on the harmonics. And they repeated topics that the reporter already mentioned earlier. And they did not bring up a lot of the error analysis for the reporter. And they also had unclear definitions for this theory, phenomenon. So for the phenomenon, the opponent asked why is the sound heard when the air passes through, and it says the reporter just replied with pass and not pass, and we believe the explanation was not enough. It is because of the change in pressure of the air when the airflow is being cut off. That is why this sound is created. So the opponent asked, did you try different angles of the airflow? And the reporter said no, but we believe that it would affect the blue circle, and the frequency won't change, but the intensity will decrease. We also agree with the reporter, and we feel like the reporter should consider this in their experiment as well. And so they also talk about how the hole size affects the sound created in it, and then they said it affects the sound intensity, and we believe that their explanation of this change in hole size was insufficient, but we do agree that the hole size changes the intensity of all the harmonics. So for the opponent asked, did you consider airflow speed? And the reporter said they consider low, medium, and high air speed. I believe that they could test different more air speeds to see the effects, because we believe that the airflow speed can affect the different harmonics and their amplitudes. So our question was that what are the relevant parameters, and the reporter mentioned a few of them, and then we did not get to, or the opponent mentioned a few of them, and we did not get to report it. And so what does the shape of the holes? The reporter says it may affect the overlapping area, and the opponent says they had no opinion on the shape of the holes. The shape of the holes can affect the sound characteristics that we collect. And so what I asked the position of the hand affect the airflow. The reporter said no, but I believe that it may affect the harmonics amplitude as well. And so their explanation of sound, both the reporter and the opponent didn't give a very clear explanation of sound. And so for points missed, the discussion, they did not discuss the basics of sound, and their understanding of sound was very limited, and I believe that they should go into the sound, because this whole topic is talking about sound. And they did not talk about vortices, vortex shedding, or turbulence, which may affect the harmonics. And they had little error analysis discussion, and they did not talk about the amplitude of the sound characteristics.
So the reporter, please present your concluding remarks.
Our concluding remarks for opponent. We think that the opponent didn't pay attention to the report because they asked too many questions that contained in the report. And when we do not spin the disc and do not use the air gun, we can get the background noise and subtract it from the experience data. And we use microphone to record the noise. And the graph has the experimental error, but the strength is the most important. And as when the frequencies that we can't hear is not analyzed. Okay, concluding remarks for the reviewer, and the cause within the cause of sound is mentioned in the report, and the sound properties explanation investigate frequency and amplitude and others. And the relevant parameters are also mentioned in the report. And the shape of the holes may affect the harmonics, but not the fundamental frequency. And that one, the position of the hands effect on the experiment is next level. And thank you.
Okay. So, any questions from the jury? Please.
I have two questions, one for opponent and one for reviewer. So can you go back, can the reporter go back to your slide 26? So the opponent, my question is that, why do you think that plot, that experimental result should decrease linearly? Slide 26. This one. Why do you think it should decrease linearly? And it shouldn't have several peaks.
Yes, it's going for a same level. There is some error or some that has wrong step in this schema and will increase this phenomenon.
Okay. And my question is to the reviewer is that you mentioned that there are several big errors in reporter's experiment. However, you only mentioned that he used the pen.
Yeah,
So anything else you should
I was going to talk about something else, but I kind of forgot what it is right now. If I think about it, I'll tell you. Okay. I can't remember what I was saying, but yeah, I was looking into other areas.
Okay, any questions from jury? Professor Wang, please.
Maybe just like this plot, you mentioned your fundamental frequency is around 400 something?
Fundamental frequency is this one.
Okay, and so the fundamental, the harmonic should be the integer multiple of this fundamental frequency. So what is the mixed harmonic in your plot? Just first harmonic, second harmonic, can you point out?
This is the fundamental frequency.
Okay.
The first overtone, second overtone, third overtone, fourth overtone, and
Are they really the integer multiple?
and the frequency is integer multiple. This frequency.
I don't get it. But for example, the first one is supposed, for example, is like 400, the next one should be 800, the next one should be over 1,000. But it looks like each point is equal distance, not really a multiple of these fundamentals. I wonder where is the harmonics in this picture. How about the opponent? What's your opinion of this spectrum? Or reviewer? Any comments?
They can analyze small points in this issue, and then we can really know what the real shape of these.
I want to say that this the list is the original data, and the peak is 1, 2, 3, 4, 5, 1, 2, 3, 4, and they are integer multiple. The frequency is integer multiple. Yes.
Very hard to see. Anyway, you didn't write down the number, right? So
Yes.
Okay, any questions? Please.
Just one quick question to the reviewer. So you asked them about the definition of the sound. So how about you?
So sound is when the sound is a wave that propagates the medium in the direction of the wave, right? So it's like vibrations or like compressions of air that are going through the medium, or compressions of the medium basically that are traveling through the air.
In that case, are you going to put another new parameter for this experiment?
No, but I feel like because this is very much related to sound, so you should know the definition of sound, because the definition of sound can help you explain this phenomenon.
Okay, because of time, let's go to the time for scoring the jury. So let's show the score for the reporter. Seven, 6, 5, 5, and 7.
7, 6, 5, 5, 7.
Let's show the score for the opponent. Six, 5, 5, and 5.
6, 5, 5, 5, 5, 5.
Let's show score for the reviewer. 7, 7, 7, 8, and 6.
7, 7, 7, 8, 6.
Also, any comment for the jury? Since no comment from the jury, then we end this point is closed. We have 10 minutes break and come back 10 minutes.
I'm ready.
Great. Okay, so please take the floor. You have 12 minutes.
After everyone, this is T Narrow. I'm going to present mechanical oscillators. So at first the content is first I will talk about problem statement, and second is experiment design, and the third one is theory explanation, and then I'm talking about my experiment, and at last one is conclusion. First, talking about problem statement. As you can see,
our main focus is on the relation between the position of the magnet and the period of the oscillation, and its initial force and time of the oscillation process. So this is experimental design, and this is our tool to do the experiment. First, you can see there's a plastic ruler, and that's our to know how the group between the magnet. And these two ruler is made of the metal, so that we can move them and go put it on the base. So there's a theoretical construction. So when the amplitudes of the two waves are the same, and the amplitude when the two are in phase will be twice the height of the either component wave, and when the two are out of phase, the amplitude and these three of these will be zero. And here is the second. We see similar motion displayed in the double pendulum. Each mass has its own beat frequency that cycle from the large amplitude to zero amplitude and back. One mass will have the highest amplitude when the other mass has an amplitude of zero. This means that the motion of the masses are grouped by the sum of two dependent wave function. It is very easy to see the two frequencies of the system as proven the total motion. All we have to look for are the two forms of the motion mode, where both pendulum move constantly with one motion and do not change cyclically. It is at these points where the one wave function is zero, such that the other is the only one acting on the system, and therefore there is only one that is the same. The first is we display the two masses with the exact same value in the same direction. Both of these two are put to move to left or right. Because of the mass are equal, the length of the springs are equal. So both the mass will move exactly as same, and they will swing back and forth equally. So in the best happening, they will have no energy loss, but here's the reality. So they will lose energy until they stop. And the second mode is if you displace mass 1 or 2 in an equal and outside way. So if you put a mass 1 magnet in the left and another magnet is right, so they will disrupt each other's energy, and then they will stop it faster. It is important here to note that the reason we get the big frequencies is because of the first and the second modes are of slightly different frequencies. The mode of the second mass will correspond to a slightly higher frequency due to the gravitatory force from the springing harmonic. So in the summary, there are two equations of motion that proven this system of the pendulums. One with a mode where both masses are moving in the same direction, and the other where the pendulums are moving in the exact opposite direction. The combination of these two modes takes up every possible beat frequency and amplitude of the system. And this equation will give the ion vectors A and B that describe the way that the two pendulums move with respect to one another. So the way to find the frequencies of the system is with this equation instead. So for the value of the And then use this value to find the angel vector and that describe that motion of the system. In this equation, Marx race at K is the statement smart mass race of the spring, and mass race N is the mass race. This is the equation used to find the angel vectors and angel vectors of the system. So there is the second math function. The math race K can be found by taking the partial derivative of the potential energy equation, and the mass race N is just the mass of the pendulums in the positions M, 11, and M. So the U is that is a kind. I forgot how to explain. It's a predicate or what? Position. Yeah. The position is made of this, and the mass raise K will equal the position. Okay, I will need the blue explanation. Once you have the K element matrices, you can solve the characteristics expression to solve for. I also don't know how to say. And once you have the values of omega. Once you have the values of the omega 1 and omega 2, you can use those to find its vectors of the system A and B, which shows the relative motions of the pendulums. So omega 1 is 0, omega 2 is okay. I'm skipping. These two results tell us that the two modes of the motion for the coupled pendulum are when the pendulums are both swinging in the same direction and when the pendulums are swinging in the opposite directions. And here's our experiment. The experiment variable. We change the distance of two magnets, number of the pole rulers, pole magnet distance, and the ruler's size. The distance of the two magnets is 8.5 centimeter and 10 centimeter. Number of pole rulers is just 1 or 2, and pole magnet distance is 1 centimeter or 1.5 centimeter. The ruler size is 90 centimeter or 21 centimeter. So the first chart is that we pull one side of the ruler and another side is just stay. And two magnets on the ruler, well, distance is 8.5 centimeter. So that is a chart we make by factor. So the coordinate x is time, and the coordinate axis y is no meaning of it. And this is the side haven't pulled. So this one is the side we pull off the ruler. This is we didn't pull off the ruler. You can see their movement is slower than the last one. And here we pull, and we also pull one side of the ruler. And two magnets in distance is also 8.5 centimeter. Fourth magnet distance is 1 centimeter, and the length of the ruler is 1 centimeter. So you can see the side of have 4 and also looks up. And the side we have 4, okay, slowly. Okay, so yeah, and we change the ruler's length to 90 centimeter, and then you can see that and that. And that's this. We pull all both of the ruler, and the ruler's length is 90 centimeters. You can see two of them shapes clearly. So in our conclusion, we observe that this phenomenon is related to the couple pattern, and when two magnets are brought close together and repel each other, the drawn patterns verge off at specific frequencies when one magnet is stationary and the other is close. Repulsion occurs moving the stationary magnet, but because of the air resistance, it will stop after a while. So we guess if there is no friction, the two magnets will always repel each other and will not stop. This is all my reasons. Thanks everyone.
Okay, so opponent, please take the floor.
Okay.
There's 2 minutes.
First of all, can you explain eigenfrequency that you mentioned in your slide?
Eigenfrequency.
Yeah. Okay. So in your set, can I see your setup image?
What?
Do you have an image of your setup?
We didn't put any image on it.
Alright. Well then I have to ask you, was the base did you put the 2 strips on one base, or was the base separated?
The base is 1, and I put 2 of the ruler.
Okay. So can you go to slide 13?
Okay.
Can you explain your variables to me?
Right. Variable is.
Alright. So on page 20, you go to page 20. So what graph is this for? Because I know this one is for
The side we pull it.
the side you.
Is it? Sorry. There is 2 sides of the ruler, and we pull the one side of it, and the other side we didn't pull it.
Oh, so this is the one you pull and this is the one you didn't pull.
Yeah.
Okay. And so, did you try different types of metal strips, or not even metal strips? Did you try different types of leaf string?
No,
You only use ruler.
Yep, you
Okay.
always use.
Did you consider different strengths of the magnet?
Oh, sorry, we didn't try.
Okay. Did you try different lengths of? You did try different lengths of the ruler, right?
Yes, we try to.
And then what did you find?
Time is up. So the opponent has 3 minutes for preparation. proponent, please take the floor.
Okay, so I'm Gary from United, and I will be opposing number 6, magnetic mechanical oscillator. So the problem statement reads: secure the lower ends of two identical lead springs to a non-magnetic base and attach magnets to the upper ends such that they repel and are free to move. Investigate how the movement of the string depends on relevant parameters. Wait, go back. So I believe that we should look into the beads and external coupling. So for the observations, there weren't many observations because they did not really show their experiment, but they did talk about how this is a coupled oscillator, and they talked about beat frequency, although I did not see much on that by the reporter. And they had a discussion of mode, which I believe is really important to this topic. And so the bad parts are that everything was very text-based, even a lot of their observations, which I believe they should actually show their observations. They did not try different selection of strips, and they had a lack of observations because we weren't able to see their observation. And yeah, and they had no setup image. So for their theory, they had some parameter change, and they believe that the wave functions are independent as they mentioned in the front, and they did not have a correction of magnetic field. They didn't talk about external coupling, and we believe that they should talk about Euler-Bernoulli's equation or some sort of Hooke's law equation for the deflection of the strips. And they had a lack of theory explanation. We did not really understand their theory. Okay, so they did. Oh, it's not the least slide, but they did change the distance of the two magnets, as well as a few other parameters. But I felt like they did not have enough changes in parameters, and so they didn't verify the restoring constant of the strip, and they didn't verify the magnetic forces. They did not talk about external coupling, which should be mentioned in the experiments, and they did say it was on the same base, but we do not know for sure because they did not show an image, and the graphs did not have axes, and we did not understand some of the graphs they had. So they didn't actually analyze the data, so we thought that they could look into how the second magnet force contribution, as well as the initial movement of non-perturbed magnet, as well as the FFT frequency of the waves, and they didn't have real data analysis. And so for the theory, we can look into damping, correction of the magnetic field, as well as Euler-Bernoulli to model this phenomenon, because their theory, I did not understand it and they did not explain it clearly, so I believe we can look into that. And for the experiments, they did not have magnetic force distance verification, and they did not talk about external coupling. And for data analysis, they didn't really have data analysis, so we can also go into that. Okay, I would like to start my discussion.
Please go ahead.
Okay, so first of all, can you try to explain your equation again? Because I did not really understand your theory for this experiment. Huh? Oh, can you explain your theory again in clearer?
Can I use the blackboard?
Please,
Yes.
please.
The theory is that here is a Q magnet here, and if I put both of them on the left,
Oh, I meant the quantitative. So you had it on your slide, right? Can you explain it again? No, quantitative, so the numbers, the variable. Yeah, this thing. So what is this model?
okay,
I
actually,
Okay, so I know that this is some sort of energy equation, but I believe that this is not enough to model the whole phenomenon. I think that the question statement can be split into two main parts. One is the deflection of the strips, the leaf strips, and the other one is the magnetic force. So, do you believe that's so? Like, I don't really see that in the equation. So let's talk about the Euler-Bernoulli equation. So, the Euler-Bernoulli equation is so epsilon naught is equal to du over dx. So this equation with some other variables can model the deflection of the strips. So basically, negative e to the times I. This is E is the Young's modulus and I is the area moment times E squared W d x squared is equal to the moment, which is able to calculate the deflection of the strip. So let's say the strip was originally like this, and when you deflect it, it becomes like this. So W of x would be this value, and so what we want to do is find, like, when you have a force here, the strip is deflecting. So when you solve this equation, you'll find that the deflection is roughly like so 6 over, and then some other constants here. So basically what happens is, so this L, because we want to find where the magnet is because of the deflection, so this L just represents the x, which is the position, but the top of the strip. And then so so what do you think the magnetic force is then? So let's say this models the deflection of the strip, right? And so I said that there are two parts, the deflection of the strip as well as the magnetic force. Do you know anything about the magnetic force of the magnets? Okay, so I would model it in some way with a constant as well as the distance of the magnets to some sort of exponential depending on your experiment. So this can be the magnetic force. And so you should, by adding these two together, you are able to find this system, the phenomenon, basically movement, I guess. Okay, so let's talk about externally coupled, external coupling. So you mentioned about the two nodes in your in this, right? Can you explain the two nodes to me again? What are the two nodes? Or two modes. Oh, modes. Yeah. You had it in your slide. I'm not too sure where it is, but you mentioned it in your slide, right? So MOEB, yes. Yeah, so can you go to your slide for me? Let me explain the two modes. So basically, there are two positions or modes where the force. So let's see here. You have two leaf springs, right? And so you see the oscillations. So a mode. The first normal mode is when you have the oscillations together, like this, or going opposite of each other. So during this mode, the forces, the Paul's statement says that the two leaf springs should be on the same face, right? So what you have two modes. This one and when they're going in the same direction as each other, right? So the common phenomenon that occurs when two metronomes are on the same surface is that due to external coupling, the two metronomes, even if they're at different frequencies, the frequencies will match up. So basically, in this phenomenon, what happens is when this is happening, when the second normal mode is happening, so this is the second normal mode, this is the first normal mode. When we have the second normal mode, it will slowly, the base of on the bottom will go in the opposite direction of the different leads, which will result in the forces canceling out. So now you will only have like the first normal mode after a while. Do you understand? Okay. So I believe that you have something about the mode. So did you do any sort of modeling?
Our experiment just with our first mode.
Oh, so you did not consider the second one? Okay. So then let's go into the frequency. Or can we look at your graphs for the motion? Yeah, so that's the second one. Or the one with both. Can you explain why this one is oscillating but this one is like this?
Okay, because this is the non-magnetic wave. We use force in it, and in this magnet we didn't give it any energy. And in the reality, there are the energy can give it to it all the energy given it. So it's spinning not like this.
Right, so, okay, we talked about how you didn't have labels on your graphs and you didn't actually know what it was, right? So you knew that this was time, right? And do you know what this axis is?
My teammate told me that it's tracker, so there's no meaning on it.
I don't agree with that. I believe that this is the position of your magnet. Because if you look here, you have like negative as in one side, and then positive as in the other one. So your magnet is oscillating like back and forth, right?
Oh.
So that's the position, the tracking of the, yeah, so then, I still don't get why this one doesn't match with that, because you realize that when the magnet, let's say one magnet is moving, the magnetic force would push the other magnet to move as well, right? So shouldn't the other one move greater than this?
It should move that.
Like shouldn't the two graphs match up to roughly the same?
It should move that.
It should, right? Okay. So I'm not too sure why this happening. And so you also talked about the beat phenomenon in your in the introduction. Can you go into that more? So can you go to like the earlier slides of the
Sorry, the time is up. Proponent, please summarize the discussion. You have 1 minute.
Okay. So basically we asked about their theory and they didn't understand the theory very well. So we modeled it as, so the opponent suggests that the reporter models it as two parts. One is the deflection of the strip, the other is the magnetic force that affects the oscillation. And so we talked about how we can use Euler-Bernoulli to model that case. And we also discussed about the magnetic force and what affects the magnetic force, but the reporter didn't really know too much about that. And we also discussed the different types of modes that the reporter mentioned, the first normal mode and second normal mode, but he didn't really know what was happening. We also talked about the external coupling, and how it affects our phenomena, and discuss about their graphs and as well as the B frequency or B phenomena.
So the reviewer, please take the floor. You can ask questions to the reporter and opponent.
So thank you for the reporter and the opponent. So my first question is, will the magnet on this side attract the other steel rule? Will that cause error?
Yes, you have error.
Wait, can you say your question?
Will the magnet on one side attract the other steel rule? Will that cause error?
Yes.
And what are the causes of energy loss?
Because of the spares in the gravity, here is a.
I mean, obviously, it's possible that the energy is transferred to heat or some sort of sound. We cannot hear or feel it, but this may be possible transformation of energy.
Okay, and do you think the video frame rate should be increased?
Obviously, if you increase it, you're able to see the oscillation. So I guess you'll have better data, but I don't think how that affects the actual phenomenon.
Okay, and so you previously mentioned that so can you prove, how do you prove what causes the energy loss?
Energy loss? Well, I mentioned heat and sound, right?
Yeah, how do you prove it?
I don't believe I can prove that because that's just a common concept.
And how do magnetic energy and kinetic energy exchange?
Can you repeat your question?
How do magnetic energy and kinetic energy exchange?
Well, the magnetic energy is pushing the other magnet, which then is changing into negative energy to move the rod.
Okay. So the review, you have 2 minutes for deliberation.
Chairman.
Okay. So review, please take the floor.
So we're from Typt, and this is problem 6. And so I think the key points of the problem statement is the model of the lead spring and magnetic force and the relationship with simple harmonic motion and the discussion of energy loss. And so this is the overview. And so for the phenomena, the theoretical and so this is the overview of the report. The parameters over and the theoretical analysis of topics and use of the charts and change various parameters. And so the suggestions is there is too much text and need to put some diagram and images. And we also think that the bit frequency should be defined first before talking about it. And it could, there should be units on the graph, and there should be a faster video frame rate to be used. And we think that, and so this is the comments for the opponent. For the advantages, they make a clarification of the variables. And the clarification should be done in 10 minutes period and not the 2 minutes period. And the opponent should focus on the theory on the slides and not to introduce new ones. And so for the discussions, we think that the reporter should focus on the slide. And so my question is, what are the causes of the energy loss? And so the opponents say the energy could be transferred to heat or sound. And for our opinion is that some of the causes are air friction and natural decay of the lead spring. And the other question is, will a magnet on this one slide attract to other steel ruler? And so opponent agreed. And the reporter said, yes, it would cause error. And opponent agreed. So for our opinion is that it will make error. Steel ruler should not be used. And should the video frame rate be increased? The opponent said we can see the fluctuation more, but that may not affect on the phenomenon. And for our opinion is yes, because the graph shown fluctuates a lot. And how do magnetic energy and kinetic energy exchange in the phenomenon? And for the opponent, they said that the magnetic energy is exchanged to the other magnet's kinetic energy, and we agree. So this is the missed points. The opponent should be focusing on the experiment and other items on the slide, and not to focus on the theory. And so the conclusion is the opponent shouldn't be talking about a theory when it's time for discussion, and not much discussion about experiment in the 10 minutes discussion. Thank you.
Okay. So, reporter, please present your concluding remarks. You have 2 minutes.
Thanks for the work of the reviewer and opponent suggestion, and I have some of the parts to review, and I should more understanding to the presentation, and I should analyze my data more seriously. So, and I also should do more better reliable for these experiments, and I should have more discussion about the different parameters. And I also have to do more discussion with the opponent. This is the end for my report today.
Okay. So any questions from the jury? Please.
I have one question for the reviewers. You mentioned that the steel ruler shouldn't be used, and how would you suggest them to use for natural experiment next time?
Maybe use it as a
Why?
because magnet doesn't, I use clay to stick the magnet because magnet won't attract the plastic glue.
Can I answer her question as well?
Sure.
Okay, so they already did use the plastic ruler, but I believe that they can also try different sorts of metal rulers that aren't really magnetic, such as brass, because different metals have different restoring force and deflection, and that may affect the experiment. So they should consider using different types of metal strips.
Any question? Please, Professor.
So you mentioned about this
Euler
Bernoulli
yes,
equation, and first you also try to understand their couple
Yeah.
model. So in your opinion, is these two models totally different, or they can be somehow
Like
related to each other?
his model
Yeah,
and my model. So obviously his model, I saw that part of the model was modeling energy, and I believe that it can be included together, but then since as I explained, I believe that the phenomenon is built into two parts. One is the deflection of the leaf spring, and the other one is the magnetic force. So I feel like he should incorporate that into his equation. But obviously he had some sort of energy equation or formula to model his experiment.
Any questions?
Okay, let me put it this way. You mentioned about being deflected, and also you have magnets. How do this affect the motion of this, how do I call it, oscillator? Okay, you have a ruler that will be deflected like this way, right? You have magnets, they are repelled to each other. And how do they affect the oscillator?
Okay, so
Just one by one, okay?
So in my opinion, like if the magnetic force is too strong, then you'll see that the magnets won't be moving too much because they'll all like bend because the force is too strong. And if the magnetic force is too little, then you wouldn't see as much of this coupling.
Do I have any influence on the frequencies?
The frequencies, let me see. When we have time to think.
How about you?
So the magnet will exchange energy between the loop strings, and the rule will show the kinetic energy.
I do believe that these parameters will affect the frequency that you see.
How about you?
Sorry, Professor, I can't.
You know, there's two magnets, they repel each other, right? And there's a ruler. The ruler is bending like a spring, okay, lift spring, okay. So there's like a spring constant K, and you have a repulsion force. So how do this affect your oscillator? I mean, the effect of these two parameters should have a strong impact on the frequencies. You observe the frequencies, right? You observe the oscillation. So the only thing you measure is period, for example, the period or frequency. So how do these two things affect the oscillator?
Here. Okay, I'm for English.
Okay, anyway. Yep.
We think that the oscillating frequency should be the same.
It'll be the same. Okay. How about you?
But I already said it's different because like if you have if your magnetic force is smaller, then the oscillations would obviously be smaller. So that leads to a smaller frequency.
Okay. Thank you very much.
Okay. So, it's time for the story adjournment. let's show the score for the reporter. Four, 5, 3, 3, and 3.
4, 5, 3, 3, 3.
Let's show the score for the opponent. 8, 7, 8, 7, and 8.
8, 7, 8, 7, 8.
And let's show the score of the reviewer. 7, 7, 5, 5, and 8.
7, 7, 5, 5, 8.
Okay, so any comment from the jury about this point? Please.
Yeah, I think for the reporter, I think you can go back to understand the gradual mechanism. Mechanics you have on slide 13 and 14. There are some mistakes on your slide.
Yeah, I know.
May I just speak?
I think this problem is really harder for high school kids.
你中文讲啊。
我完全没有看过他的理论，我连他的仪器完全都没看过。
Okay. Anyway.
So let's finish the file this afternoon. Let's give everyone here a big hand. Okay.